Walk into any kitchen and you are surrounded by highly specific engineering choices. You have copper pans, wooden spoons, aluminum foil, and rubber mats. Try frying an egg on a wooden pan or stirring boiling soup with a solid copper spatula, and you immediately see the problem. The objects fail because the materials fail. Every item here is built from a material selected for its distinct physical properties, the observable physical traits that dictate exactly what a substance can and cannot do. By testing how different materials react to light, heat, and physical force, we can sort almost all matter on Earth into two major categories: metals and nonmetals. Knowing how to spot these hidden physical properties turns an ordinary kitchen into a visible map of the rules governing the material world. The first test is visual. When you look at a clean piece of silver or copper, it shines. This is metallic luster. The internal structure of the metal catches light and reflects it brilliantly. Compare that to a piece of coal or a block of wood. These materials absorb the light that hits them, leaving them with a flat, dull appearance. You might see a reflection on a plastic container or a glass window, but that is a smooth surface gloss. True metallic luster comes from the material itself, not just how it is polished. Next, we test for hardness. If you try to scratch or bend an iron pipe, it fights back. Metals generally retain their shape and resist damage under physical stress. But if you apply enough force, like striking hot iron with a heavy hammer against an anvil, the metal doesn't shatter, it flattens. This ability to be hammered or rolled into thin sheets without breaking is called malleability. Nonmetals cannot survive that kind of impact. Hit a lump of sulfur or a piece of chalk with that same hammer, and it simply crumbles into powder. We call this trait brittleness. Because metals are both lustrous and malleable, we can pound gold into ultra-thin decorative leaf or shape steel into car doors, manufacturing tasks impossible to achieve with brittle nonmetals. Inside the walls of your home, electricity is traveling through miles of narrow metal threading. Those threads exist because of ductility. Ductility is a material's capacity to be pulled and stretched into a continuous wire without snapping. But nonmetals completely lack this molecular flexibility. If you try to pull a piece of carbon or solid sulfur into a wire, the tension causes it to snap almost instantly. We can also test materials by listening to them. Drop a coin or tap a steel plate, and you hear a distinct lingering note. Materials that produce a clear, sustained ringing sound when struck are known as sonorous. Cast metals, like the dense iron or bronze used to make bells, hold these acoustic vibrations beautifully. Try striking a piece of charcoal or a wooden block, and you get a dull, flat thud that fades immediately. Between their ductility and sonority, metals prove they are highly efficient at carrying physical energy and sound waves across a distance. That efficiency extends to heat, too. Leave a metal spoon in a bowl of hot soup, and within minutes, the handle burns your fingers. This is thermal conductivity. Rapidly vibrating metal particles pass thermal energy efficiently up the handle. Wood lacks this internal structure, so it stays cool. Metals also conduct electricity. Their structure allows electrons to flow freely from end to end, much like water rushing through a pipe. But we need nonmetals to control that flow. Insulators, like the rubber or plastic wrapped around an electrical cord, block those electrons, keeping the current safely inside the wire. The natural world does have a few anomalies that challenge these neat categories. We call them the rule breakers. Take mercury. It has a bright metallic luster, but it completely breaks the rule of hardness. It is the only metal that is a liquid at room temperature. On the nonmetal side, graphite is dull and highly brittle. Yet if you hook it up to a battery, it conducts electricity with ease. Because a material might have one unusual trait, relying on a single test is not enough. Scientists have to check for conductivity, luster, and malleability together to classify a substance accurately. Look back at the kitchen. None of the tools here are accidental. Their materials were selected because they pass specific physical tests. The pans and foils are metallic, lustrous, malleable, ductile, sonorous, and excellent conductors of heat. The spatulas and mats are nonmetallic, dull, brittle, and reliable insulators that protect us from burns and shocks. Scaling up, the smartphone in your pocket relies on a precise combination of dozens of these elements. using metals for wiring and nonmetals for casing, working together perfectly. Pick 3 objects in the room around you. Based on what they do, can you predict if they are made of metals or nonmetals?